Hi, this is Ms. Nickel, and I'm going through problem number 17 on the Newton's Laws Test 1. This is the retake version, but if you have the other version with the truck pulling the trailer, same ideas are going to apply to that. So this is a classic problem in physics. It's called a horse pulling the wagon. And if you understand how to solve this problem and how it works, this means that you have a pretty firm grasp of Newton's laws of motion, which is what we really want you to have. So that's why this problem is so important. Okay, so what is the first thing we do when we're solving this problem? I'm going to go ahead and highlight the variables like I do in any physics story problem. So I have a 650 kilogram horse, mass of the horse, mass of the cart, and an acceleration for both the horse and the cart. So I'm going to write those in and make it clear. I'll just label them this way. This is mass of horse, mass of cart, and acceleration of the horse, which is equal to the acceleration of the cart. So those are the variables that we have. Part A asks us to label the physical diagram. And to do that, I'm just going to draw a horizontal line. First here, just level with the horse and the cart to kind of give myself a guide. And we know that the cart is being pulled, so there's a force of the horse on the cart, right? That's going to be the action force. I'll put a dot here, center of mass of the cart, and that's a pull force, so it will go from the center and forward like that. And I'm going to label that as force of horse on cart. Now I know there has to be an equal and opposite reaction force and that it has to act on a different object. That's going to be the backward pull of the cart on the horse. That's going to start from the horse's center of the mass. The line should be equal and opposite, even if I don't quite make it equal. And I'm going to label that as force of cart on horse. So I have those taken care of. Now the horse is accelerating forward, right? So we know that there has to be a forward push on the horse to make it do that. And the way that works is the action-reaction pair there is actually with the ground. So the horse is pushing backward on the ground with a certain amount of force, right? This is going to be force of horse on ground. And the ground is pushing forward on the horse. And that's actually what's causing the horse to move. As it pushes backwards on the ground pushes forward on it. So we can label this as force of ground on horse, which is going to be the same as the total force exerted by the horse, right? Because they're equal and opposite, although its total force is actually exerted backwards against the ground, okay? But that's why I was just calling that the total force exerted by the horse. You'll notice that is greater than the force required for the horse to pull the cart, and that makes sense since the horse is also accelerating, so it needs additional force to accelerate itself, and that's going to be the net force on the horse. We're going to call that F net, and that's just going to be this portion of that total force. I'm going to draw just an approximate line there, F net, and that's the force that is actually accelerating the horse and not just being used to pull the cart. Okay, so we are going to be using Newton's second law, and that law, simply stated, is force equals mass times acceleration. We know that we can write that a couple different ways. We can write it as acceleration is equal to force divided by mass, or mass is equal to force divided by acceleration. Okay? But we're really just going to be using this version of it. Pretty straightforward. The part B in this problem then says, what is the force exerted by the horse on the cart? And I think this is where you get kind of confused because you're thinking, oh, the force is being exerted by the horse, so it must have something to do with the mass of the horse. But if you think about it a little more carefully, it really doesn't, right? Because if you have a heavier cart, the horse has to exert more force to pull it with the same acceleration. And if you have a lighter cart, the horse has to exert less force to pull it with the same acceleration. So what it really depends on, what the force the horse has to exert depends on, is the mass of the cart, not the mass of the horse. And we can rephrase this question then as how much force is required to accelerate the cart at 1.8 meters per second squared. That makes it a little easier to think about, right? So what we're looking for is force of horse on cart, and that's going to be equal to the mass of the cart times the acceleration of the cart. And we have both of those things. So we're going to set this equal to 420 kilograms, the mass of the cart, times the 1.8 meters per second squared that we know the cart is accelerating. And if we solve that, we get 756 newtons. Remember that force is a vector quantity. This is positive because it is going to the right. We always assume right is positive unless I tell you otherwise in the problem. Now the next question is really easy because we can just use Newton's third law here. What force does the cart exert on the horse? So the horse is pulling the cart forward. The cart is going to pull backward with a force equal in magnitude and opposite in direction. That means that the force of the cart on the horse is just going to be equal to negative 756 newtons. Okay, same magnitude, opposite direction. Now we're going to get into that net force I mentioned a little bit earlier. That's just the portion of the force that is used to pull to or accelerate the horse. And that's a little more clear if we look at it this way with just a block. And we did a few of these on the test also, and I kind of talked you guys through them because I think it's something we should have gone through more in class. And so if I have a block with some different forces acting on it, let's say we have the weight of the block. That's a force, right? Force of weight is equal to the mass times the acceleration of gravity. And here I'm just going to say that's negative 5 newtons. And I have my normal force acting upward to counteract that. That's 5 newtons. So I have no acceleration in the y-axis because my net force, F net y, is 0. Now, what if I have a 20 newton force acting to the right and I have a 5 newton force acting to the left, like that, right? We'll call that negative 5 newtons then, since it's going to the left. That means that I have a net force to the right of 15 newtons because we're taking the vector sum, right? Remember, force is directional. That's a vector sum. So F net in the x direction is going to be equal to 15 newtons right or positive 15 newtons. So think of this as the horse and the cart problem, right? We've got this backward pull, but that's going to cancel out a portion of the rightward push. But our net force is only going to be the portion of that force, actually be a little bit more like this, that is causing the object to accelerate. Net, and that is going to be equal to the mass of that object times its acceleration, because the object will be accelerating if there are unbalanced forces acting on it. If there was no acceleration, F net would be equal to 0. So let's take a look at the horse and wagon problem again, and looking here at this picture then, F net then is that portion of the total force pushing the horse forward that is causing the acceleration. So it's just that portion causing the acceleration. So therefore it's going to be equal to the acceleration of the horse times the mass of the horse. So F net for the horse is going to be equal to mass of the horse times acceleration of the horse. So that's going to be equal to 650 kilograms times 1.8 meters per second squared. which comes to 1,170 newtons, and that is positive, is acting rightward in this diagram. And that's the end of the horse and the wagon problem. Hopefully you have a better understanding of action-reaction forces and net force by working through this problem, and I'll provide some other resources as well. See you in class.